Hello fellow problem solvers. So today we're going to be doing a problem from the 2013 IMO, problem number 4. I suggest you try this nice geometry problem out for a minimum of 45 minutes, ideally 90 minutes to 2 hours, not more than 4.5 hours. And this you should especially try out. If you want to go along with us, try it out for a minimum of 10 minutes to sort of see what the problem is about. And it's a great problem if you're just getting comfortable enough to you're almost like there. You want to try to do a geometry from the IMO, do this problem. It's a bit on the maybe medium-ish of the easy ones, but it's a great problem anyway. So now without further ado, let's begin. And the first idea is, okay, let's see what's going on here. Draw a diagram. What do we have? A, B, C. Okay, we're going to have W is going to be a variable point on BC, lying strictly between B and C. So we're getting that this is an acute triangle. This is just something that's important to know in general. The reason they're telling us this is so that we don't have to talk about the case when it's obtuse or acute because the orthocenter is inside or outside the triangle, right? Just trying to give us the substance instead of dealing with many cases. When it doesn't tell you this at the IMO, just be aware that there might be something about these other cases that you might not have the full problem if you don't cover the other case. So just keep that in mind in general. And let's see, what do we have? We have, okay, the feet of perpendiculars. Okay, and then we draw these X and Y. Okay, so let's now, how will I draw the diagram? Well, I'll put A on top, B and C here. Why? Because this problem statement is symmetric with respect to B and C. So because I want to have, it's easier for me to have this, like this be my sort of axis of symmetry, if I think that's the term, instead of it being, no, maybe this, actually this being my axis of symmetry, that these two things are symmetric, right? It's easier for me to have it be this way. And now, okay, I have these feet of perpendiculars, I have H, I have B, C, A, and I have M and N, B, W, N. Okay, so W is going to be here. And now let's see, X is really a point such that this angle right here is 90, and so is this. Okay, that's X. And then Y is its corresponding cousin here. Okay. With this problem, there are a couple of approaches we can take. And I'm going to invite you to pause for 5 minutes and think, like, draw your first conclusions from this picture, from this problem. How would you prove that X, Y, and H are collinear, right? Try to draw your first conclusions for the next 3 to 5 minutes. And here's the first thing for me. There are a couple of approaches. One is, let me calculate some angles. And I'm saying, okay, this is 90, 90. Okay, so this is gamma. This is always 90 minus gamma. This is beta. This is always 90 minus beta. Where else do I have 90 minus beta? I have that here, 90 minus beta. I have, if this angle is X, I have the trouble with W is that, mind you, if I have this angle X, the angle C and W, the angle BMW is sort of fixed, it's defined, but I don't think I have it. I don't know how to calculate it. Maybe I can do some sines and cosines, but I don't really have it. And that's what's difficult and puts into question any sort of angle chasing here, that I might need to do something else. So that's the first thing I see. I have X, and I have to say this is Z, 90 minus Z. And now I'll have to look for something here. I'm also thinking, what happens when I put W close to B? Then I'll get these. But yeah, like you're trying to see like these extreme cases or specific cases. What if W is at L? This like perpendicular from A to B, C, call this point L. What if this is our W? What if W is the midpoint? What happens to X and Y? How does this line move around? Like, these are all questions that I'm asking myself. Because if you think about it, X and Y are going to be on these perpendiculars to BC that go through points B and C. That's where X and Y are going to be. And the idea is, if I pick a Y here and I draw an X, like there's a unique W on this side. So there's some thinking going on there. I'll need to draw a better diagram to see more angles. But here I want to also talk about computational techniques. Namely that this is a great problem to try out with analytic geometry or just a plane coordinate system. And here's why. The reason why you'd want that is I'm going to pick, I have these 3 points, W is on BC. So BC is going to be my x-axis. I have 2 degrees of freedom. I can fix 2 points to be specific numbers. And I'm going to fix A to be 1. So this will be, L will be 0, 0 for me. And A will be, so its x component is 0 and its y component is 1. Why would I do this? Now think about it. It's easier now for me to calculate n. B is going to be xb and 0. This is going to be xc and 0. I'm going to calculate n. It's not going to be beautiful, but it's going to be doable. And then for x, I already know its x component. Same thing for y. I only need to figure out their y components. And why do I only need to figure out their y components? Well, because I am trying to prove I have these 3 points. I have their all perpendiculars, right? All of them are perpendicular to BC, like h's, x's, y's. And I'm trying to prove these 3 points are collinear. Now, take 5 minutes and think about what is enough for me to prove. And here's the answer. What I have to prove is that this over this is the same as this over this. Why? When I put 90-degree angles here, I'm going to get right triangles. And this is also a 90-degree angle because this is parallel to this. And actually because this is parallel to this, the way I've drawn it. Both of these things are the case. Actually, they're at a 90-degree angle. But if I prove these two, if x, h, and y are collinear, looking at the problem backwards, and I have the sum of these angles is 180. In other words, if this is x, this is at 90 minus x, which means this is x. Which means these triangles are similar. How can I calculate, what are these lengths? This is xb, actually this is negative xb. This is xc. This is going to be the y component of y minus the y component of h, the y component of h minus the y component of x. And that's it. And if I prove that these are this over this is this over this, then I have similarity and then I'm done with the problem. And now it's a lot of computation and it would take some, and you need to do this actually when you're solving these problems. You evaluate how long the computations will take and whether they will be difficult or not. X, I have n and m defined as these feet of perpendiculars. I can define x as a point such that this is 90, the point which has the x component which is equal to xb, and that is at a 90-degree angle here. And it's going to, this is going to be a variable point, so it's going to be some t and 0. Right, that's going to be its x component. And now we calculate this. And then we'll finish up. Okay, that's one way of going about it. What? You want me to do the calculations? It's going to take half an hour. Really? Okay, let's do the calculations. So the computation that happens is this. This took me about between half an hour and an hour to complete. And to double check this, I made a mistake. I made a mistake twice as I was doing this and need to start all over. But if you're careful with your algebra, maybe you don't need to make that mistake. So how do I begin? I first state A is 0, 1. L, the height from the feet of the perpendicular from A to B. C is 0, 0. And then I have B and C. I put BC to be my x-axis because of what I mentioned previously, that it's going to be easier for me to get x and y. And then because I know their x coordinate, I only need their y coordinate then. So the first thing now to do is to figure out what n and m are. And the great thing about this also is that because I have xb and xc, they are symmetric. So if I get n, because m is defined symmetrically, I'll immediately get m. And I can even claim that that is going to be the case. And similarly, because m and n are symmetric, so are x and y, right? If, for example, if b is say n is a function of xb and xc, like f of xb xc, then m is f of xc xb, right? Because it's the same thing that m is, like, these two things are the same. M is for b, the same thing n is for c. And similarly, x is for b, the same thing that y is for c. So then we first do this. Now we're trying to calculate. We know the x coordinates of x and y, and we're looking for the y. We find these slopes, and then through some algebra, we equalize, we get that. This perpendicular condition gives us that the slope of wn is equal to the slope of minus 1 over the slope of nx. And through this algebra, it simplifies to actually something nice. It gives us that x is this really xb times t minus c. And then what we'll have for the opposite one for y, we'll get that its y component is xct minus xb times c, right? You just switch the x and b. The t stays the same, t being the, what's it called, the x component of w. And now with that, we just finish up with our similarity. We're trying to show that this over this is the same as this over this. And in that case, when we draw the perpendiculars, we will have similarity, i.e. we'll have this angle is equal to this one. So this one is 90 minus x, this is 90, i.e. x, h, y are collinear. And this turns into showing that both of these things are true because when we get xb minus xc is xb minus xc, which is true. And this is how we do the computation. Now, let's get back to the more nicer approaches that we could have done. And now we're back after those calculations, right? That was good. It was a big ride. We said a lot of stuff, and it took me a while to do those calculations, and now we can get back to trying to solve the problem in a better way, right? So now let's actually draw a better diagram with that, clear this part up, and try to see if there's other ways that we can solve the problem. And we have this thing right here, right? This is our diagram. Now let's actually calculate these angles. That is the first thing you sort of need to do in geometry to sort of see what it is you have. So let's try our luck. Maybe just let's look at x for now, and then the analogous thing holds true for y, right? This is the great thing about symmetry, and why you should notice symmetries in your geometry problems, because then you know, okay, I just need to look at x. And what I find for x, I can find the same thing for y. And now let's do some angle chasing here. And the first thing that sort of comes to me is now, okay, once I've labeled this x, I have this angle is also x. So now I have this angle is equal to this one, x and x. And I'm using the condition that this is 90. It's always important to keep track that you're using the conditions of the problem. Now what I also have is 90 minus beta here. And I have 90 minus beta here as well. So I have similarity. Now let's keep that in mind. So let's actually see, like we have x, b, n. This triangle, xbn, is similar to the triangle w. At b we have 90 minus beta, at c we have 90 minus beta, and n is where we have the x. Or n is also, I think, correct me if I'm wrong, but I think this is a center of some spiral symmetry perhaps. Perhaps, I don't know, to be frank, but it's like you can see it's like taking this triangle, expanding it, then like rotating it to get to this one. Might be some center, I don't know. But now we have that these xbn, and why is this cool for us? Well, now I have that xb over wc is equal to bn over cn is equal to xn over wn. And now why is this useful potentially? And the answer is, well, back to this idea right here. We really only care about figuring out what xb is in terms of some elements of the triangle and w, because that's what it depends on. It depends on w. And here, we can actually get that. And I invite you to pause for 5 minutes and think about, how would you get that? How would you write x? And the answer for me is, I wouldn't write it through this. I'd write xb is equal to wc times bn over cn, right? And now I have yc is analogously going to be equal to wb times cm over bm. And now what is it that we have to prove really? Well, let's get back to our little L here. We need to prove what? Pause for 10 minutes and try to push this idea forward now. We're trying to think for 2 minutes of what we need to prove. And the answer is, well, we need to prove that. So what is our triangle going to be? We're going to have x, so we're going to have xb. We're going to have hl minus xb. That's going to be the size of this over bl. Will need to be equal to yc minus hl over cl. Okay? Now, what do we know with respect to the elements of the triangle? So there are many ways for us to do this. The quickest way, we can do similarities here. I'm thinking whether we should do similarities or just plain trigonometry. But let's actually first fix this up a bit. This is true. This is what we have to prove. Question mark. Is this true? If we're looking at the problem backwards, it has to be true. But this is true if and only if HL times 1 over BL plus 1 over CL, if this thing is equal to what? XB plus Y. XB over BL. XB over BL plus YC over CL. Okay, so now let's write this in terms of this. XB over BL, we need an over BL, over CL, over CL. This is the thing that's question mark again. What is this going to be? So first and foremost here, what we're going to have BL times CL in, like when you get them to the same denominator, and in the numerator we're going to have BL plus CL. That's BC. So we're going to have BC times HL over BL times LC, right? We're going to have this is going to need to equal, okay, so what do we have? BL, CL. Let's write this in terms of this. I'm going to have what? WC times BN over CN, everything over BL as well, plus, so let's now think we have BN, CN, and BL. Okay, now here, I want you to actually, there's a cool way for us to actually now finish this, I'm seeing. So WB over CL times CM over BN. Okay. CL over. Okay, BL, CN, BN. Okay. So now my question for you is, what can we do with this? Like, WC and WB are going to be variable. And this is something that is fixed. So we need to show that when we add these up together, we get something that's fixed. How are we going to do that? Well, let's see. We have BN over CL. Okay, this is a triangle with beta and 90 minus beta. Where else do we have such a triangle? The answer is here, 90 minus beta. In fact, these triangles are similar, right? And how are they similar? We have B and C, this triangle. B and C is similar to the triangle BLA. And now what do we have? We have BN. Okay, we're going to have BN. let's do Bn over Cn. Bn over Cn is going to be equal to Bl over La. So now what do we have here? Bn over Cn, 1 over Bl. So we have this thing is equal to 1 over La. And then similarly, and also symmetrically, this is going to be equal to 1 over La. So this is a question mark, but we know this thing is equal to now Vc over La, or Wc over La times Wb over La, which is La, and here we have Wb plus Wc, Bc. So now we need to prove that La times HL, so we need to prove that this times this is equal to this times this. How are we ever going to do that? Pause for 2 minutes and figure it out. There's loads of ways. My favorite would be to reflect H with respect to Vc and use power of points because H prime is on the circle of ABC. But that's needlessly complicated. It's needlessly no showing off. But I would here just say, okay, I have, what do I need? I have BC, and LA. Here I have, actually no, BC is gone. I need to have HL times LA is LC times LB, right? Okay, let me write this as a fraction. LA over LB is equal to, what is it going to be? LB, LC over LH. Okay, so now I have LC, LH. Okay, LA, LB. So what is it that I need? Well, LC and LH, well, this is a triangle with beta and 90 minus beta. Oh, wait. What is this? A triangle with beta and 90 minus beta. And so we are done with similarity. Ba-dum. Again, and then similarity saves the show. So now because we have the similarity, we have that this, in fact, is equal to this, which is equal to this, equal to this. And from there on, we get this similarity we wanted here. And we are done with the problem. However, this is again kind of a bit too computational, bit too, let me just solve the problem for my own personal taste. I frankly am not a huge fan of this solution. It's good that you know these types of solutions, that you can see different types of solutions in geometry because different problems will lend themselves to different solutions. And having a wide variety of solutions that you know can help you solve problems which, say, aren't going to be susceptible to analytic geometry, or here aren't going to be susceptible with similarities, but really I could have also done this trigonometrically more quickly, but I mean actually not necessarily more quickly. With similarity, I just needed to make sure what I was doing, right? That I was actually getting closer and closer to these triangles. I needed to combine them, and it's actually better than I thought it would be. Now, the difference with trigonometry, let me just say that, is instead of writing Bn over Cn, I would write, okay, Bn over Cn, well, that is 1 over tangents beta. That's pretty much it. And then I would use the fact that what is also 1 over tangents beta, Bl over La is also 1 over tangents beta. Like I would use that again somewhere else. Like it's really a shorthand, more so than using any trigonometric identity. Like I did all this through similarity, trig would just be simulating it. Now the big here idea for me was, instead of calculating these angles, is to say, okay, wait a second. We have these circles. And this idea also will go to show another important idea in geometry. Something that applies regardless of what the problem is. And that is when you draw a good diagram, ideas pop up. Now what is the idea here? There's also background theory that can pop up in geometry special with that, but here an idea pops up. And if you draw the second diagram, you'll also see this being the case. W. So this point of intersection here of the two circles, why is it interesting? Well, it's interesting first and foremost because BNMC are also concyclic. And so by the radical axis theorem on omega 1, omega 2, like this is omega 1, this small w is called omega 2, and it's this lowercase omega. And that's your lesson of Greek for today. So we have omega 1, omega 2, and B and M, C are concyclic, so by the radical axis theorem, these 3 points meet, which means if we call this point Z, we have these are collinear. Now what is also the case for Z? Well, we know that Wy is going to have 90 with anything that's on the circle. So Wzy is going to be 90. And it's the same with Wzx. So Z is already on this line. So on this line xy. So now maybe we need to look at, maybe Z is our bridge between what it is what we want to prove and what we already have. So what else holds for Z? Pause for 2 to 5 minutes and see what else holds for Z. We paused and saw that, wait a second, this angle is, the whole angle is going to be 180 minus gamma. This one's going to be 180 minus beta, which means this angle is 180 minus alpha, which means Z is also on the circle with A and M, on the circle around A and M. But H is also on that circle. And furthermore, AH is the diameter. So that means that HZA is also 90. And this finishes off the problem. Because now we have YZW is YZA is 90, and HZA is 90, so these 3 are collinear. And XZW's XZA is 90, and HZA is also 90, so again, we are done. And this shows that these 3 points are collinear because they all have the same angle with respect to A. Or in this case, they sum up to 180. And this finishes off the problem. And this is why the problem is actually very, very cool in my mind. Now, the thing about these 3 different solutions. First, the purely analytic geometry one is, I have no idea how to do this, but I can see I can compute this. So let me just, and it's going to take me roughly half an hour to an hour to double check my work. However, the issue with analytic geometry is, one, if you go in, you need to go all in. There's almost, I think always, there's no partial credit for analytic geometry. 0. Like here, if we didn't solve the problem, but we had Z, if we just wrote down Z, like introduce the point Z, or if we just introduced this similarity, if we wrote down this similarity, we would get partial credit, like almost without a doubt. Just introducing Z can give you a point, right? That's how these things work, usually. Now, and actually, they worked like that when I was competing. I think they still work like that because they give you like little points. Like I got in 2015 on problem 3, I proved the lemma, and I got a point. And a friend of mine didn't prove that lemma, and that point cost for bronze medal. So partial credits do exist, and there can be sometimes very dumb partial credits, or not dumb per se. They can be just like it can be low-hanging fruit, not as difficult as much as the whole problem is difficult. So that's one thing. The second solution teaches you just how to do similarities or trigonometry, seeing again this thing, this is what is enough, and noticing again that you have these at a 90-degree angle, that all of these are parallel, and that's very, very nice when you have all of these are parallel. Even if they weren't at a 90-degree angle, I believe, let me just double check, if they were all like this, yeah, you could still do 90-degree angles here, and you would still have a nice time, right? If you could now calculate this, so that would be a tad more difficult given this is not a 90, but I want to say it's doable-ish. Maybe if this angle is nice, maybe trigonometrically, though I'm not sure. But given they are all, perpendicular to BC, it's much easier. It's a lot easier. Maybe there's actually some, maybe if we did this, the parallels to BC, still there could be something that's doable there if this is nice to compute. Actually, this thing would be nice to compute. The only question is what this would be. Actually, no, my bad. Forget about 90. We just have them parallel to this, BC. It would still be nice, right? And it's important to have that sort of thinking also, like what is enough for me to prove, okay, sort of, let me forget about A. Let me look at these as points, like this. Like what's enough are these heights. And the third way is, I think, more generalizable, and it's also, I think it's more beautiful. That's why also I'm biased a bit to say it's more generalizable, because it says, okay, first, when I draw a good diagram, this Z makes a lot of sense. To me, this Z makes a lot of sense regardless of the diagram, and here's why. A couple of reasons. One is this X, Y, Z are collinear. Number two is the fact that A, Z, and W are collinear. When I can have a point which has so many things, I want to introduce that point. Another thing is, Z will be called, you might read this somewhere, the middle point in the triangle ABC of the points M and W. It just means that whenever you have this situation, like this circumcircle, like omega 1, omega 2, and we call this omega 3, if you have 3 points on these sides, then, and define these circles omega 1, omega 2, omega 3 like this, whatever the 3 points are, if you're on N is on this, on AB, M is on AC, and W is on what's it called, BC. Then omega 1, omega 2, omega 3 meet at one point. They meet at a shared point. And this is angle chasing, and this also works if they're like over here. It works like this omega point can be out. This point Z, called the middle point of these 3 points, can be outside. It can be all over the place. And it's a very cool thing to know that there's that background knowledge which leads me to do that. But for me, I think it's really just knowing that these 3 are collinear. And when I saw that these are collinear, and I'll get consecutive points, I was immediately excited. But then when I know, oh, these lie on the same circle, but H is also in that circle, and it's like, wait a second, this point is connected to X, Y, and H, because initially, X, Y, and H, there's nothing in common with them. What they have N and B, that's what X and H have in common. Nothing else. What's the connection between W and H? There's zero connection, right? And symmetrically with Y and H. But if you think about X and W, what's their connection? Not X and Y. What's their connection? The answer is W. Nothing else. But this point sort of gives a connection for all 3 of them. And that's why I think it makes a lot of sense to put it in the problem. Now, this solves our problem in 3 different ways. I hope each way sort of tells you a different flavor of thinking, even analytic geometry, though it's big. I did that computation. Please appreciate it. And as always, thanks for problem solving.